Alright guys, welcome to Unit 4, the periodic table and periodicity. Periodic table obviously is what the big thing is hanging in your classroom, and periodicity is the fact of how all the elements work on the periodic table. You have the word period there, that root word, is talking about repeating. So like if a periodical is like a newspaper, it comes every day. So the word period there is because the properties of the elements repeat, and so that's why you get this shape of the repeating elements. You also know from the last chapter that the shape is due to the electron configuration. You have the S block, the P block, and the D block, so don't forget that as well. So we've got a bunch of elements. Elements come from all over the place. This is kind of just for fun, but you had some elements that everybody knew about, things like sulfur, tin, carbon, and copper. Then you had some elements that are named for places. You have francium, polonium, germanium, gallium for Gaul, the area of southern Spain, europium for Europe, americium, America, californium for California, and scandium for Scandinavia. Have some named for some famous people: Einsteinium, obviously, fermium for Enrico Fermi, Mendelevium, which you're going to find out about in just a second, Mendeleev, Nobelium, Alfred Nobel, inventor of dynamite, Lawrencium, Rutherfordium, which you might remember from the gold foil experiment, Ernest Rutherford, and borium for Niels Bohr and his orbital model. Some are just in foreign languages. You have tungsten, iron, gold, silver, lead, tin, and copper. And one of the coolest things, you have mythology related names. You have thorium for Thor, and promethium for Prometheus, thallium for Tal, titanium for the Titans, and palladium for Paladin. And then you have mercury and xenon, which are related to some of those elements' properties. Real quick, you have Dmitry Mendeleev, who's probably one of your coolest pictures you're going to see of a scientist. Most of them look the same. Dmitry Mendeleev looks kind of like a wizard. But he's a Russian dude, and he was given credit for the first periodic table around 1870. He didn't know a lot about the elements, but he knew that they repeated, and so he figured he could put them in order. And he organized the table by increasing atomic mass. And not only did he do that, but some elements didn't even exist, and he left blanks for those elements, and he predicted what those elements were going to be like. Periodic table we have today, though, was created by Henry Moseley, and a little bit more normal looking dude. But he put the elements in order of increasing atomic number, which is how they are arranged right now on the table in your classroom. Periodic law just says that every so often the elements repeat. A period is your horizontal rows. There's only 7 periods, and they refer to the energy levels. It's easy to remember because a period goes at the end of a sentence, and you write a sentence from left to right horizontally. Then you have your groups, also called families. Families go from from top to bottom. These are your vertical columns. There's 18 of them, and groups is how things share properties. Periods don't share properties, they just share size. Groups share properties. On the left side of the table, you have your metals. Metals form cations, and if you remember from a couple chapters ago, a cation, or from last chapter, a cation is a positive ion, one that has more protons than electrons. So metals will give up their electrons to satisfy the octet rule, and so you have metals on the left side of the periodic table. They are lustrous, they are ductile, they are malleable, and they're good conductors of electricity because you have electrons flying all over the place. Nonmetals on the right side of the periodic table, they form anions because they accept electrons. Some of their properties is they're good insulators, which means electricity and heat don't go through them very much. And most of them are gases or either brittle solids. You got neon, sulfur, iodine, and bromine. So some regions on the periodic table. You see metals on the left, which is most of the periodic table. This is your metals. Then you have nonmetals on the right, plus hydrogen, which hydrogen acts weird. Hydrogen and helium kind of both act like they're on both sides all the time. But hydrogen is your one non-metal on the left. But then you have this line in the middle where you have metalloids, semi-metals. This is in this shape kind of like a stair step. And on a lot of periodic tables, you'll have the stair step actually drawn on the periodic table. If they're touching that stair step, except for aluminum, they're a metalloid. And metalloids actually have the properties of both things. And I think I'm getting stuck here, guys. Sorry. But yeah, there's a list of your metalloids. Boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. Properties are in between those. They're silicon and germanium. They're semiconductors. And they're really good to use with computer chips because you need computer chips to be able to turn on and off. And sorry, my slides are acting up here. Come on, slides, let's go. There we go. So, computer chips for your metalloids. Here's some other groups. Alkali metals are group 1. You're going to draw a picture of this, or you're going to do this on a blank periodic table in class. Group 1, they're very reactive. The alkaline earth metals, group 2. Halogens, group 17. Oh, a little over there, sorry about that. Noble gases, group 18. Lanthanides and actinides, don't really worry about. Those are your bottom 2 rows. We don't really deal with those because they're the f orbitals, and they're big guys that break a lot of our rules. Another name we don't really worry about is the coinage metals. That's group 11. That's one where you have metals that are really good at making coins out of because they're cheap. Then you have your transition elements. That is very important. Groups 3 through 12, their charges can change, so you don't have to know the charges for groups 3 through 12. Whereas the main block elements, those are the ones you have to know the charges for. Groups 1, 2, and 13 through 18. So just filling that out real quick, you have hydrogen, you have your alkali metals, you have your alkali earth metals, you have your halogens. I'm not sure why alkali earth metals and noble gases decided not to show up. Well, there's noble gases. But you'll do all this in class, so don't stress out too much. And like I said, I apologize for my slides being a little strange today. You have your transition elements, all there in the middle, metalloids, your stair steps. Then you have your representative elements, which are groups 1, 2, and 13 through 18. Just to show you how it's all filled out. Sorry about that. Like I said, we're going to do this a lot in class, so don't stress out. We'll have plenty of time to go through all this stuff. If you have the same number of valence electrons, you're going to have similar properties because you're going to want to either take or lose electrons a similar way. Look at lithium and sodium. Lithium has the highest energy level is 2, so it's got 1 valence electrons. Sodium, highest energy level is 3, 1 valence electron. So in any group, the element below has 1 more occupied energy level than does the element above. So lithium, 2 occupied energy levels. Sodium, 3 occupied energy levels. So the only difference though is the size, because they're going to act the same because you have 1 valence electron that it wants to get rid of and 1 valence electron that it wants to get rid of. So some trends that we're going to have. First off, atomic radius. As you go down the periodic table, the atomic radius gets bigger. That's obvious. And it's the size of a neutral atom. You get bigger as you go down because you're adding energy levels. You're adding energy levels, your elements are getting bigger. The electrons are farther away from the nucleus. And there's my atom getting bigger. But here's what's kind of strange. That atoms actually get smaller as you go left to right. And it has to do with a process called Coulombic attraction. And Coulombic attraction is just a fancy way to say attraction between positives and negatives. You know that electrons are negative, protons are positive, and the more we get of both of them, the more attraction you're going to have that actually pulls the atom closer together. So just kind of showing you how Coulombic attraction works. It depends on the amount of charge, so you have greater force between 2 and 2 than you would between 1 and 1, and also the distance, so you have greater force when it's closer together. So just kind of demonstrating here, a hydrogen atom has 1 proton and 1 electron. A helium atom has 2 protons and 2 electrons, so it's going to squeeze closer together. So even though the hydrogen is even though the hydrogen has a mass of 1 and the helium has a mass of 4, the helium's atom is actually smaller because the whole atom pulls closer together without adding another energy level for your electrons. So as you go to the left, you get more Coulombic attraction, no new energy level, so you get actually a smaller atom. So your smallest atom on the entire periodic table is helium, whereas your largest atom on the entire periodic table is francium, all the way to the bottom on the left. Shielding effect is just a force that makes it so you have electrons that are on the inside, called kernel electrons, are going to shield against the valence electrons on the outside. So it's kind of the opposite of Coulombic force. Coulombic force is positives and negatives. Shielding effect is negatives and negatives. And so if you have a negative beside a negative, it actually pushes it away. And so you end up with these electrons here getting a shielding effect from the positive center of the atom. The bigger your electron, the more shielding effect, and so the easier a valence electron is to pop off. So as you go down, you get more shielding effect. Ionic radius works a little bit different. Now, the previous radius we talked about was neutral atoms. Ions are things with a charge. So cations, let's look at an example. You have calcium. Calcium has 20 protons and 20 electrons. Now, a calcium ion is going to actually no change on protons because you can't change protons. How do you become positive 2? You become positive 2 by losing 2 electrons. Now, if you look at this, there's 2 electrons less. Since there's 2 electrons less, the protons can pull them in tighter, and you end up with a smaller atom. Also, those 2 electrons were on the outside energy level, so cations get way smaller. Anion, let's look at an example for that. 17 protons, 17 electrons. A chlorine ion is going to have 17 protons, but it had to be a -1, so it actually has 18 electrons now. There's no new energy level, or actually there is a new energy level, but you're adding an electron, and the protons can't pull it in as hard, and so you get a bigger atom. Anions are larger. Ionization energy is the energy required to remove an energy from an electron. So the first ionization energy removes the first electron, second ionization energy removes the second electron, and so on. So each successive ionization requires more energy than the previous one. So pretty much it's a little bit easier it's a whole lot easier to remove the first electron than it is the second electron, and there's very few atoms that are going to let you get a third or fourth electron. So you have your hammer, then your sledgehammer, then your excavator. So as you go down, the first ionization energy decreases because you get a bigger atom, you get more shielding effect, so it's easier to pull an electron off as you go down the periodic table. And as you go to the right, shielding effect increases because you're getting more electrons on that outside energy level, so atoms are less likely to want to get rid of an electron. So kind of like go back to what we said with the size, the most ionization energy, the most ionization energy on the whole periodic table would be at the top on the right. So helium, you are not getting an electron off of helium, whereas the lowest ionization energy on the whole periodic table is francium because it will slip and fall and accidentally give you an energy. Electronegativity is kind of like ionization energy except for backwards. Ionization energy is how much energy it takes to get an electron off. Electronegativity is the tendency for a bonded atom to attract an electron to itself. So ionization energy is how easy it is to get an electron. Electronegativity is how hard it is, how easy it is to remove an electron off, how bad an atom wants to steal an electron. As you go down, electronegativity decreases because you have way more shielding effect, and that positive force can't get to the electrons. And as you go to the right, electronegativity increases except for your, sorry about that, guys. Finish up this conversation about electronegativity. So except for your noble gases, because noble gases don't want any electrons at all. Fluorine has the highest electronegativity on the periodic table. Fluorine is Mr. Steal your electron. Fluorine will come and grab an electron anywhere it can, whereas francium wants to give away an electron, so it certainly doesn't want to get an electron. So it's all about these trends on the periodic table, which we'll spend a whole lot of time with over the next couple weeks. Sorry about my stuff messing up, and I hope you enjoyed your video, guys. Thanks.